Hello, and welcome to this video series of StressOff, where we conduct finite element analysis of a 1 cubic meter steel cube with a pressure of 1 megapascal on the top face and different boundary conditions on the bottom face. The software that we are going to use today is online. It's called Simscale. It can be accessed from www.simscale.com. You need to create a free account and just click on new project, give it a name. Let's say case 01 cube. Project description will just say StressOff video series. For the category, we'll say learning and teaching, and we'll just add a tag of StressOff and video series. Let's create this project. We'll wait for it to generate a project for us, and then we'll be taken up to the project folder. Now it is asking us for the geometry. The geometry I've already created here, or we did create when we conducted the finite element analysis using FreeCAD. So I have created two different files. One is a step file and the other one is an STL file. We can import both. So how about we just import a step file? So once when you put your file up there, you can click on import and the file will be imported soon. Now the file has been imported, so let's just go in and we can have a look at the geometry, and you can see that it is roughly, well, you can see that this geometry is 1 meter in width. In Simscale, z-axis is pointing in vertical direction, so we will make sure that z is up. Now we just click on create simulation. Now here we are going to create a static analysis. We'll click on create simulation. So the analysis type we have selected is static. Geometry has already been selected. Now element definition is there, model is already there. We need to add a material. Okay, so let's just go in and select steel and click on apply. We'll just change it to 2.1. And the Poisson's ratio will change it to 0.3. Now once when that is done, we'll just click on save. We'll then go in and add boundary conditions. So let's first start with fixed values. So here, first of all, we are going to add the bottom face with dz of 0. We'll unconstrain dx and dy. So that is dz 0. And then next, let's just go in and add a pressure of 1 megapascal on the top face. Click on OK. Next, we will have to click on mesh. Now we can decide on the sizing of it. What we want is, remember that the entire length or the edge of the cube was divided into 10 parts, and the only way we can do is by giving 0.1 as the edge length. For minimum, we'll just add 0.05 and we'll just say generate. As you can see, mesh has been created. The only thing is here the number of nodes or the number of elements are different. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 and 16. So the number of elements are a bit different. And how about we just say 0.1 as the minimum length and 0.1 as the maximum length. Let's say what it does. And meshing is finished. Let's just check the number of elements. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So it hasn't changed. How about we'll just accept whatever mesh is given by default and just add a simulation run. We'll just say start. And wait for it to finish the simulation. As you can see, the simulation run has failed, and we probably know what would be the problem. Bottom face was not constrained properly. So how about we go in and we constrain the bottom node by some more fixed values? Well, it looks like we cannot add one particular constraint on the edge of the block. So instead of putting the constraint on the edge of the block, how about we just go in and select this whole face and let's put in dx equals to 0 and let's just call it dx0. Let's change the name of this one as dz0 and let's create one more of fixed value, call it dy0 and make this face as dy0. I'll just quickly check that dx is proper, dy is proper and dz is proper. So all of the boundary conditions have been set now. So let's go in and add another run and let's start this. Now as you can see, Simscale was able to finish this simulation. So let's quickly go in and post-process this result. What we are mainly concerned with is the displacement and 1 Mises stresses. So if we want to change 1 Mises stresses to megapascals, we can see that 1 Mises stresses are 1 megapascal for the entire cube. Instead of 1 Mises stresses, we can go in and have a look at the displacement magnitude as well. Again, we would just go in and let's go for millimeters. This is the right way. So for displacement magnitude, and as this face, the right face and the front face were constrained, the displacement more is on the opposite side face or edge or corner, and all of the other displacements are fine. The maximum displacement on this side you can see is 5.173 micrometers. What I'm more interested in is displacement in z direction. Now this displacement is consistent throughout the entire height of the cube. When I say consistent, it means it is gradually increasing from the bottom to the top. Now at the top, the maximum displacement in Z direction is minus 4.762 micrometers. Now let's go in and again check 1-my stresses before we go in and conduct the analysis again using the bottom face as fully restrained. So let's go back, and how about we delete dz0, dx0, and with dy0 we'll delete that as well. Let's go in and add a fixed value. We can just give a fixed support. Fixed value would be same. So we go in and add fixed value dx, dy, dz0 for the bottom face. And let's just say fixed. And then let's run a third simulation. As the simulation has finished, let's go in and quickly conduct post-processing and check what are the results for us. As you can see, in Z direction, 1-my stresses are high on the corner of the bottom face, and the maximum on the corner is 1.347. Let's change it to megapascal. So it is 1.347 megapascals at the corner nodes, and on the center of the bottom face the value of 1-my stress is 0.5634 megapascals. On the top it is even, roughly around 1 megapascal. Let's quickly go in and check displacement magnitude. Displacement magnitude here, you can see it is maximum of 4.759 micrometers in Z direction. Again, this is displacement magnitude. If we go in and check in Z direction, it is showing minus 4.644 micrometers. So that's the finite element analysis of 1 cubic meter cube using Simscale as the software. The entire simulation we were able to conduct online. So the core or the computer that I used, it can be anything. It can be a Chromebook, it can be a Windows 7 computer. As long as it has latest browser in it and you have an account with Simscale, you will be able to conduct analysis. To learn how to conduct finite element analysis using different softwares, stay tuned and be with us. Thank you all. Bye for now.